Good morning, or afternoon, or evening. My name is Yannick Sztamfater. I will be presenting some of my PhD progress so far and a small recap of the research day that I'm currently on. So, essentially, I'm in third year officially, but realistically, I'm actually in second year because it's really the second year that I'm able to fully focus on the PhD, because the first year I was kind of involved in a master's, which pretty much took most of my time. My first supervisor is Joaquin Miguez from the Department of Teoría de la Señal, and my second supervisor is Manuel Sanjurjo from the Aerospace Engineering Department. So, as a brief recap of the research activities that I've undertaken so far, I've attended two conferences, one at ESA in 2023 and the SciTech conference in Orlando earlier this year, and I'm in the process of submitting a paper to Acta Astronautica, which I will be sending it over in like 2 days, 3 days. My supervisor has to review the conclusions basically, but it's pretty much there. And I'm currently doing a research stay at UC San Diego. There's a picture of the San Diego skyline for you to enjoy. I've never seen it yet because I'm always on the other side or studying. But yes, so my work essentially deals with the problem of space situational awareness, SSA, which essentially focuses on two aspects. One of them is accurately tracking spacecraft as they orbit around the Earth. And we do this by the use of particle filters or sequential Monte Carlo filters, and also applying stochastic as opposed to deterministic propagation schemes to better account for the uncertainty associated to the estimation process. And also, the second topic is, which I will be presenting today, is the computation of the probability of collision between two space objects by the use of reduced dimension modeling and variance reduction techniques such as rare event theory, importance sampling, and so on and so forth. So the motivation for this topic is the fact that we are surrounded by more and more space debris. This is only getting worse with time because there's more and more objects that are being launched into space, such as the space satellite infrastructure that is being launched by Starlink, SpaceX, or anything to do with telecommunications, and basically the number is just increasing exponentially, increasing the risk of further collisions, which would increase the amount of space debris and things that could collide with other things. So it's a massive problem, so it needs dealing with. Another thing is asteroids, which are gaining, well, they've always been very attractive as an idea because people want to know just how likely it will be for an asteroid to impact with the Earth. Not very likely, but it's something that definitely occupies people's minds, and a lot of money is invested into near-Earth orbit object detection and the risk of impact. So the current status of the operational methods to compute the probability of collision between spacecraft, they are good for now, as in they are efficient and they're able to compute a probability of collision, but these methods often are efficient because they rely on assumptions that may not always hold true in practice. Some of these assumptions are outlined here, which essentially include the objects traveling in straight lines when they collide. There are uncertainties being modeled by Gaussian distributions when they at time of collision. Another one is neglecting completely the velocity uncertainty and the fact that spacecraft are not spherical. They usually have strange shapes, but they're assumed to be spherical. Well, so we aim to propose a method which will bypass some of these assumptions, hopefully. But first, we'll introduce the problem. So the problem is you have two spacecraft, right? A and B, in their orbits around the Earth. Each spacecraft state is assumed to be given by a distribution, an initial distribution at time zero, which may perfectly be Gaussian, or you can assume to be Gaussian. So it's given by a mean value, which is this x with a hat, and a covariance matrix. the C, and we model them as being a joint object. So we model the two distributions as a joint distribution of the form of this third line here, which is the normal given by the mean of the two states and the covariance of the, so it's a 12D state essentially. Next we have another element is the propagation of the states forwards in time to detect a collision. This will be from time 0 to time t, and this will obviously remain in the same 12D space, but it will take a different value, right, depending on where you are. So the conjunction metric that we proposed essentially aims to, it models by exploiting the geometry of a Keplerian conjunction. It aims to essentially extract where collisions are more likely to happen, or where collisions are going to happen, which is going to be in the nodes of intersection of the two orbiters, as we see in the diagram here. Obviously, if the orbits don't intersect, then there will be no collision. So two conditions must be met for this collision to occur, which are given by the two equations here, which essentially we are able to reduce the problem to just studying the distance radially, so from the center of the Earth to where the spacecraft is, the distance between these two spacecraft radially, and the angular position, the angular difference between the two spacecraft at this line of nodes, which is the line in the middle. If these two conditions, if these two variables are 0, then there is a collision. Of course, there is a threshold around the 0, which is associated to the size of the objects, essentially. So now we're able to map the 12D state onto 2D, onto the 2D space, so given by the two variables here. So we're able to compute these two variables along the propagation, and we can extract our 2D variable, or 2D metric here, which is composed by the gamma and the delta. Here is an example of a conjunction plane for a particular test case. We see in the propagation in time, if we save up the 2D values throughout the propagations, we see it gets pretty close to 0 if you see the 0, 0 mark, but it doesn't actually collide. So this is an example of a non-colliding spacecraft scenario. To recap, we have a propagation model, which might be any fidelity you want, Keplerian being the lowest fidelity. So we have a mapping from 12 dimensions to 2 dimensions, which is Keplerian mapping, seen on the first line. But Keplerian dynamics don't usually yield very good, very accurate results, especially in low Earth orbit, where there's a lot of perturbations. So you need a high fidelity mapping to capture all the wobbling and squishing of the objects around their orbits. The thresholds that we impose on this 2D space are different depending on the orbital regime that you're at. If you're in Leo, your threshold is going to be 10 to the minus 6, depending on the size of the hard body radius, which encompasses the two spacecraft, and the distance from the spacecraft to the center of the Earth, which is also different in geo. You're much further out, and so this threshold is going to be smaller. So we have any kind of fidelity mapping. If you use a high fidelity mapping, which is usually required, then it's going to be costly. One way that we use to bypass this is that we essentially, I'm running out of time. Okay. We essentially approximate this high fidelity estimate by pretending like the high fidelity is composed as a Keplerian low fidelity plus some correction. So we're able to essentially do a first order approximation around a particular value, and we're able to map a distribution from time 0 to the collision time. So now we can cheaply only estimate high fidelity for a few samples and extract the relationship required to map a whole load of samples onto the 2D space. By crude Monte Carlo, if you're going to just do a bunch of high fidelity propagations, then it's going to be very costly. So we do importance sampling, which essentially uses a distribution that is not the one given, but one that will give you a collision with some prior knowledge, you're able to derive this. But obviously, if you just do loads of samples and see how many land in collision, if this proposal is going to land in collision, then you're going to obtain a biased result. So you give these samples weights, and I'm rushing over this. I know it's probably not going to be very clear now, but if you go over the slides, then hopefully that will make a bit more sense. So the probability of collision equation is the one that we can see here, which is essentially the same for the Monte Carlo, but including the weights. So I'm going to skip this validation really quickly, but we're able to see that the distance between the two space objects in 12D space is small when the 2D metric is small, which is what we want. So if it's 0 or around 0, you want it to be collision or small distance, which is what we see by the color coding here in the 0, 0. And our proposal, when mapped onto the 2D space, the approximate model, when evaluated in high fidelity, we see errors on the right of the order of 10 to the minus 11 and 10 to the minus 8, which means that our approximate mapping is able to compute accurate results. The probability of collision is close to the crude Monte Carlo, which makes no assumptions, but at a much lower computational cost. So we're able to essentially get a similar accuracy to CMC, crude Monte Carlo, at a much lower cost, and bypassing loads of the assumptions that regular probability of collision methods employ. Research stay at UC San Diego will be for around 4 more months, co-supervised by Dr. Aaron Rosengren and Boris Kramer, who each specialize in a different topic of my project. One of them will be astrodynamics, and the other one is the statistics part and the rare event sampling. And the goal will be to essentially expand this methodology to include asteroid conjunctions, better propagation models, and essentially an alternative to the linear approximation, so bypassing that completely by modifying the framework of the importance sampling approach. And that'll be all. Sorry for going over the time. And yeah, have a good day. Goodbye.